Imagine a world where the flow of events could be, in a sense, rewound. Not for people or for history, but for waves. Think of light or sound or radio signals. For decades, scientists have pondered a curious idea. They wondered if waves could reflect not just in space, but also in time. This concept, known as time reflection, was a fascinating theoretical puzzle. It suggested that a wave could be sent back along its own path, effectively reversing its temporal journey. This idea remained largely in the realm of mathematical equations and imaginative discussions. It was a concept that stretched the boundaries of our understanding of wave physics, promising a new dimension of control over the energies that shape our universe. The prospect was tantalizing, but the practical means to achieve it seemed far beyond our grasp for a very long time. This theoretical dream, nurtured for over half a century, has now stepped into the light of reality. In the bright days of May 2025, a remarkable announcement echoed through the scientific community. Researchers confirmed the experimental existence of time mirrors. This was not a subtle effect, hinted at in complex data. It was a clear, demonstrable phenomenon. The confirmation marks a significant leap forward. It transforms time reflection from an abstract notion into something tangible and controllable. The news sent ripples of excitement across various fields of physics and engineering. It was a moment that many had anticipated, a testament to persistent inquiry and innovative thinking. The implications of this discovery are vast, potentially reshaping technologies we rely on daily. The journey to this point was long and filled with intellectual challenges. The very idea of reflecting something in time sounds like it belongs in science fiction. However, physics often explores concepts that initially seem counterintuitive. The theoretical groundwork laid down over many years provided a roadmap. It outlined the conditions under which time reflection might be possible. Scientists meticulously studied the behavior of waves. They explored how waves interact with different materials. They theorized that if the properties of a medium could be changed incredibly rapidly and uniformly, then a wave traveling through it could be forced to reverse its temporal direction. This precise, swift change was the key that remained elusive for so long, a formidable barrier to experimental verification. What does it truly mean to have confirmed time mirrors? It means we have unlocked a new fundamental way to manipulate waves. This is far more profound than simply making a wave bounce backward. It's about controlling its evolution in time. It is about taking a signal and sending a copy of it back towards its origin, not just in space, but as if time itself were running in reverse for that wave. This breakthrough, achieved by a dedicated team of researchers, opens a new chapter in physics. It offers us a powerful new tool. The ability to create and control time reflections could lead to innovations previously unimaginable. The universe, it seems, still has many wonderful secrets to reveal about the nature of time and waves. We are all familiar with ordinary mirrors. You stand before one and it reflects light. Your image appears to be behind the mirror, looking back at you. This is spatial reflection. The light waves bounce off the surface of the mirror. They change their direction in space. If a ball hits a wall, it bounces back. This is also a spatial reflection. The ball changes its path through space. The core idea is that the wave or object encounters a boundary and reverses its spatial trajectory. It travels away from the boundary in a new direction. This is a fundamental interaction we observe constantly in our daily lives, from seeing our reflection to hearing an echo in a large room. Time reflection, however, is a profoundly different concept. It is not about changing a wave's direction in space. Instead, it's about changing its direction in time. Imagine recording a piece of music. If you play it backward, you hear the notes in reverse order. This is an analogy for time reflection. The wave itself is forced to retrace its steps in time. It is as if the wave's own internal clock starts running backward. The end of the wave becomes its beginning, and its beginning becomes its end. This is a much more subtle and complex manipulation than simply bouncing a wave off a surface. It involves altering the very fabric of the medium through which the wave travels, at a precise moment. Consider listening to a sound. If it hits a wall, an echo might return to you. That echo is a spatial reflection. The sound wave traveled to the wall and bounced back. Now, imagine that sound wave, instead of bouncing, suddenly starts to play itself in reverse, from the last sound it made back to its first. This is closer to what a time mirror does. The wave doesn't just turn around in space, its entire temporal sequence is flipped. This means that if the wave was, for example, increasing in frequency, like a siren approaching, the time-reflected wave would be decreasing in frequency, as if the siren were now receding in time. This frequency shift is a key characteristic of time reflection. The analogy of looking into a mirror and seeing your back instead of your face offers another way to grasp this. With a normal mirror, you see a spatially inverted version of yourself. Your left is your right. With a time mirror for waves, the wave's history is inverted. The part of the wave that arrived last is reflected first, and the part that arrived first is reflected last. This is not time travel in the sense of sending objects or information to the past. Rather, it is a sophisticated manipulation of wave properties within a specially engineered environment. It's a swift flip in the medium's characteristics that causes the wave to behave as if time were reversed for it. The groundbreaking experiment that brought time mirrors from theory to reality was led by Dr. Hadi Musa. His team worked at the Advanced Science Research Center, ASRC, at the CUNY Graduate Center in New York City. This institution is known for its cutting-edge research in various scientific disciplines. Dr. Musa and his colleagues embarked on a mission to achieve what many thought was nearly impossible. They aimed to create the precise conditions necessary for time reflection of electromagnetic waves. Their work required immense precision, innovative engineering, and a deep understanding of wave physics. The success of their experiment is a testament to their dedication and ingenuity. The core of their experimental setup was a specially designed device. It was not a simple mirror in the conventional sense. Instead, it was an engineered structure, a metamaterial, designed to interact with electromagnetic waves in a very specific way. The experiment involved sending signals, essentially radio waves, into this device. The crucial part was what happened next. The team needed to change the properties of this metamaterial almost instantaneously. This change had to be uniform across the entire material. This rapid, synchronized transformation was the key to creating the time reflection effect. It was a significant engineering challenge that had stymied previous attempts by other research groups around the world for many years. To achieve this rapid change, Dr. Musa's team employed a clever strategy. Their metamaterial, a strip of metal, was embedded with a series of electronic switches. These switches were connected to capacitor banks. Capacitors are devices that can store electrical energy. At a precisely chosen moment, these capacitors discharged a burst of energy into the metamaterial. This burst of energy dramatically and quickly altered the material's electrical properties, specifically its impedance. Impedance is essentially the resistance a material offers to the flow of electric current. By carefully controlling this sudden energy dump, the team could modify the impedance of the entire metamaterial strip almost instantly and uniformly. The timing and magnitude of this change were critical. The researchers needed to adjust the system's impedance very precisely. In their experiment, they found that by doubling the impedance of the metamaterial at exactly the right moment, they could achieve the desired effect. When an incoming electromagnetic signal encountered this sudden, drastic change in the medium, it behaved in an extraordinary way. Instead of just bouncing off or passing through, a portion of the wave was forced to reverse its direction in time. It was a stunning validation of theoretical predictions, a moment where equations on a page became a physical reality in the laboratory. The success of Dr. Musa's experiment hinged on a special kind of material known as a metamaterial. Metamaterials are not found in nature. They are artificially engineered structures. Their properties come from their unique design and structure, rather than their chemical composition. Scientists can design metamaterials to interact with light, sound, or other waves in ways that are impossible for natural materials. For instance, metamaterials have been used to create invisibility cloaks, at certain frequencies, and superlenses. They offer an unprecedented level of control over wave phenomena. In this case, the metamaterial was tailored to enable time reflection of electromagnetic waves. The specific metamaterial used by the CUNY ASRC team was a carefully constructed strip of metal. This strip was not just a plain piece of metal. It was intricately designed and embedded with numerous electronic switches. These switches were the active components. They allowed the researchers to change the material's properties on demand. Think of them as tiny gates that could be opened or closed very quickly. By controlling these switches simultaneously across the entire length of the metal strip, the team could ensure that the change in properties was uniform. This uniformity was crucial. If the change happened unevenly, the delicate time reflection effect would be disrupted or lost entirely. Connected to these electronic switches were capacitor banks. Capacitors are like small, fast-acting batteries. They can store a significant amount of electrical energy and then release it very rapidly. In the experiment, these capacitor banks were charged up. Then, at the precise moment the incoming electromagnetic wave was interacting with the metamaterial, the switches were triggered. This caused the capacitors to discharge their stored energy into the metal strip. This sudden influx of energy dramatically altered the electrical environment within the metamaterial. It was this rapid and synchronized energy dump that effectively changed the material's impedance, its resistance to the electromagnetic wave. The ability to rapidly and uniformly change the impedance of the entire metamaterial was the key innovation. Previous attempts to demonstrate time reflection had struggled with this aspect. It is incredibly difficult to make a material change its fundamental properties so quickly and evenly. If one part of the material changes before another, the wavefront gets distorted and the time reflection fails. Dr. Musa's team overcame this by using this sophisticated setup of a metallic strip, precisely controlled electronic switches, and powerful capacitor banks. This engineered system provided the necessary conditions for the incoming wave to experience a time boundary, compelling it to reverse its temporal journey. Section 5. How it works. The mechanics of temporal reflection. The mechanism behind time reflection is fascinating. It relies on a sudden and significant change in the medium's properties, specifically its impedance. Impedance can be thought of as the difficulty a wave encounters when traveling through a medium. For electromagnetic waves, this relates to the electrical and magnetic properties of the material. In the CUNY ASRC experiment, the team engineered their metamaterial to allow for a near-instantaneous doubling of its impedance. This rapid change is what creates the time boundary that the wave interacts with. It is not a physical boundary in space but a boundary in time, defined by this abrupt shift in the material's characteristics. When the incoming electromagnetic wave, carrying its information encoded in its shape and frequency, encounters this sudden doubling of impedance, something remarkable happens. A portion of the wave is reflected, but not in the way it would from a normal mirror. Instead, it undergoes time reversal. The entire wave packet essentially flips its temporal profile. The part of the wave that entered the time boundary last is the first part to emerge in the time-reversed copy. Conversely, the first part of the original wave to encounter the boundary becomes the last part of the time-reversed wave. This is the essence of the wave reversing its flow in time. A crucial consequence of this time reflection process is a change in the wave's frequency. When a wave is time-reflected, its frequency is not preserved, it is transformed. The new frequency is related to the original frequency and the properties of the time boundary. This frequency conversion is another distinguishing feature compared to simple spatial reflection, where frequency typically remains unchanged, or changes slightly due to Doppler effects if the mirror is moving. The ability to control and induce such frequency shifts is one of the exciting potential applications of time mirrors, offering new ways to manipulate signals. This transformation is a direct result of the wave interacting with the rapidly changing medium. It is important to clarify that this phenomenon does not imply time travel for macroscopic objects or sending messages to the past. We are not talking about building a time machine in the popular sense. Time reflection, as demonstrated, is a sophisticated wave manipulation technique. It involves a swift, controlled flip in the physical characteristics of the medium, causing a wave to propagate as if time were running backward for that specific wave segment. The information encoded in the wave is time reversed, but it still propagates forward in the grand scheme of universal time. The team's work shows we can now create and study these time-reversed waves in a controlled laboratory setting. Section 6. A Journey Through Time, From Theory to Tangible Reality. The concept of time reflection is not a brand new idea suddenly appearing in 2025. Physicists and engineers have been discussing its theoretical possibility for over 50 years. For half a century, it has been a topic of academic papers, thought experiments, and intense debate. The underlying mathematics suggested that if one could manipulate the properties of a medium in a very specific, rapid, and uniform way, then waves passing through that medium could indeed be reflected in time. However, translating these elegant theories into a working experiment proved to be an immense challenge. The conditions required were so extreme that many doubted if they could ever be practically achieved. One of the primary obstacles that researchers faced for decades was the difficulty of inducing a sufficiently fast and uniform change in a material's properties across its entire volume or surface. For time reflection to occur cleanly, the medium must transform almost instantaneously. If the change is too slow, or if different parts of the medium change at different times, the wave will simply scatter or be absorbed, rather than being time reflected. Early attempts often struggled with this requirement. Materials didn't respond quickly enough, or it was impossible to synchronize the change perfectly across the device. These practical limitations kept time reflection in the realm of theory. Dr. Hady Musa's team at CUNY ASRC managed to surmount this significant barrier. Their innovative use of an engineered metamaterial combined with fast electronic switches and capacitor banks provided the breakthrough. This setup allowed them to change the metamaterial's impedance with the necessary speed and uniformity. This achievement is a testament to advancements in materials science, electrical engineering, and experimental physics. It showcases how progress in one area can unlock possibilities in another. The ability to precisely control materials at such small scales and rapid timescales was crucial for turning a long-standing theoretical concept into a demonstrable reality. The confirmation of time mirrors is therefore a landmark achievement. It signifies more than just a clever experiment. It represents the culmination of decades of intellectual effort, and the overcoming of substantial technical hurdles. It moves time reflection from the pages of physics journals into the tangible world of the laboratory. This opens the door for scientists to now explore this phenomenon in detail, to test its limits, and to begin harnessing its unique properties for new technologies. The excitement in the physics community is palpable, as this discovery not only validates a long-held theory, but also provides a powerful new tool for manipulating waves in ways previously confined to imagination. Section 7. Revolutionizing our world. Applications in communication and computing. The ability to create time-reversed waves opens up a fascinating array of potential applications, particularly in the fields of communication and computing. In modern communication systems, signals like radio waves or light pulses in fiber optics carry vast amounts of information. The precise control of these signals is paramount. Time mirrors offer a completely new way to manipulate these signals. Imagine being able to take a complex data stream, encode it in a wave, and effectively rewind it, or make it jump to a new frequency band with high fidelity. This could lead to more robust and efficient communication systems, capable of overcoming interference or noise in novel ways. One of the key features of time reflection is the accompanying frequency shift. When a wave is time reflected, its frequency changes in a predictable way. This property could be exploited to design advanced frequency converters or filters. For instance, in crowded wireless environments, signals could be shifted to less congested frequencies on the fly using time reflection principles. This could significantly improve the capacity and reliability of wireless networks. Furthermore, the ability to create a time-reversed copy of a signal might be useful in correcting distortions that occur as waves travel through complex media, effectively healing the signal by playing its distortions backward. In the realm of computing, particularly optical computing which uses light instead of electricity for calculations, time mirrors could offer new functionalities. Manipulating light pulses in the time domain with such precision could lead to new types of logic gates or memory elements. While still highly speculative, the concept of a wave tracing itself back, as suggested by time reflection, hints at possibilities for novel data processing techniques. The ability to control the temporal shape and sequence of optical pulses with this level of sophistication could unlock new paradigms in how information is processed and stored, potentially leading to faster and more powerful computing architectures in the future. The broader implication is that we now have a new fundamental tool in our wave manipulation toolkit. Engineers and scientists can start thinking about how to incorporate time reflection interfaces into existing and future technologies. This could lead to devices that can sculpt wave packets in both space and time with unprecedented accuracy. For example, this could be used to focus wave energy with extreme precision, or to create complex wave patterns for specialized applications. The journey from this fundamental discovery to widespread technological integration will take time and further research, but the initial possibilities are truly exciting for advancing how we transmit and process information. Section 8. Expanding horizons, sensors, imaging, and photonic frontiers. Beyond communication and computing, the implications of time mirrors extend to other advanced technological areas, including sensors, imaging systems, and photonic devices. Highly sensitive sensors often rely on detecting minute changes in waves. Time reflection could offer new ways to enhance the sensitivity or resolution of such sensors. For instance, by manipulating the temporal properties of probing waves, it might be possible to extract more information from a sample or to detect weaker signals that are currently lost in noise. This could have applications in medical diagnostics, environmental monitoring, or industrial process control, where precise measurements are critical. In imaging, the ability to control the time evolution of waves could lead to new techniques. Imagine an imaging system where waves are sent into a complex scattering medium like biological tissue. The scattered waves become jumbled and difficult to interpret. Time reflection principles might offer a way to unscatter these waves, effectively creating a clearer image of what lies within. This is related to concepts like time reversal focusing, which has already shown promise. The precise control offered by the newly confirmed time mirrors could push these capabilities even further, enabling higher resolution imaging in challenging environments or even deeper into opaque materials. The field of photonics, which deals with the generation, detection, and manipulation of light, is another area ripe for exploration with time mirrors. Researchers are already conceptualizing time cavities or temporal waveguides. Just as a normal optical cavity traps light between two spatial mirrors, a time cavity might trap a wave between two time boundaries, causing it to bounce back and forth in the time domain. This could lead to unusual interference patterns and new ways to store or manipulate light energy. Such photonic devices could form the basis for novel optical components with functionalities that are currently unattainable, pushing the boundaries of what's possible with light. Furthermore, the potential for novel data storage elements, though challenging, remains an intriguing possibility. If a wave can indeed trace itself back in time, as suggested by the time reflection phenomenon, it hints at mechanisms where information could be stored and retrieved in fundamentally new ways. While the practical hurdles to creating such data storage are immense, the underlying physics is now experimentally confirmed. This opens a new avenue for theoretical and experimental investigation. The ability to control the temporal dimension of waves with such finesse could eventually lead to breakthroughs in how we manage and preserve digital information, though this is a more distant prospect. Section 9: The Path Forward. Future Explorations and Quantum Whispers. The experimental confirmation of time mirrors is not an endpoint, but rather the beginning of an exciting new journey in physics. Now that the phenomenon is measurable and controllable, physicists are eager to explore its limits and nuances. One immediate direction for future research is to push the technology to higher frequencies. The initial experiments were conducted with radio waves, but extending this to optical frequencies, light, would open up a much wider range of applications, especially in photonics and ultra-fast signal processing. Adapting the technique for different types of waves, such as acoustic waves or even quantum mechanical spin waves, is another promising avenue that could yield novel discoveries and applications in diverse fields. Refining the experimental setup itself will also be a key focus. The abruptness and uniformity of the change in the medium's properties are critical for efficient time reflection. Future work will likely involve developing new metamaterials and switching mechanisms that can achieve even faster and more spatially uniform transformations. Researchers will also investigate how to creatively handle wave interference using combinations of spatial and temporal interfaces. Imagine crafting complex space-time boundaries that can sculpt waves in 4 dimensions, 3 spatial and 1 temporal, with unprecedented precision. This could lead to entirely new classes of wave-based devices with exotic functionalities. Beyond the technological implications, the discovery of time mirrors may also prompt a re-evaluation of some older physics theories concerning time reversal processes and the fundamental symmetries of nature. While the current experiments do not violate any known laws of physics, they provide a new experimental system for studying time-related phenomena at a very fundamental level. This could offer fresh insights into concepts within quantum mechanics and electromagnetism, where the arrow of time plays a subtle but crucial role. The interaction between classical wave phenomena and quantum effects in such time-varying media could also be a rich area for future theoretical and experimental exploration. The excitement surrounding time mirrors is a reminder that the universe is full of wonders still waiting to be uncovered. This breakthrough, born from decades of theoretical curiosity and recent experimental ingenuity, underscores the power of persistent scientific inquiry. As researchers delve deeper into the intricacies of time reflection, we can anticipate not only new technologies but also a richer, more profound understanding of the fundamental laws that govern waves, energy, and perhaps even the nature of time itself. The journey ahead promises to be filled with discovery, innovation, and a renewed appreciation for the intricate dance of physics in our cosmos.